Hello everyone, I'm Shweta, MSc in Physics from RAE Mysore. So in this video, we are going to learn about carbon nanotubes. So let's proceed. Discovery of carbon nanotubes. Carbon nanotubes were discovered in 1991 by the Japanese electron microscopist Sumio Iijima. So while he was studying the material deposited on the cathode, during the synthesis of fullerenes, he found that there are other varieties of graphitic structures which was found and it has not been observed previously. So these newly observed structures are a new allotrope of carbon atom which did not just end up with the soccer-shaped molecules, these also formed long cylindrical tubes. So it was named as carbon nanotubes. So these tubes were originally called as Bucky tubes and now are known as carbon nanotubes, and in short people say CNT. So these are like a tube-shaped form. So CNT, carbon nanotubes. So they have unique physical and chemical properties that chemists are still trying to understand it better through laboratory researches. One of the physical property of carbon nanotube is that it is possible to make them only a single atomic layer thick. So it's almost 1 by 50,000 the thickness of the hair. So imagine how thin it is. So coming to the types of carbon nanotubes. So basically carbon nanotubes are of two types, single walled carbon nanotube and multi-walled carbon nanotube. So we'll see what is single walled carbon nanotube. So as you can see from the picture, it is the normal hexagonal structured lattice which is rolled up into a cylindrical form. And here the carbon-carbon bond is fairly fixed. So there are certain constraints in the diameter of the cylinder and the arrangements of the atom in it. Moving on to multi-walled nanotubes. So it is of two models. One is the Russian doll model and the other one is parchment model. So in Russian doll model, you can see that these are sheets of graphite. So many sheets of graphite are arranged in a concentric manner. Whereas in parchment model, only a single sheet of graphite which is rolled around itself. So this resembles like a rolled up newspaper. And based on the geometry, carbon nanotubes are classified into various forms. So there are three unique geometries of carbon nanotube. One is armchair, whose configuration is n, n. The other one is zigzag, whose configuration is n, 0. And the third one is chiral, whose configuration is n, m. So you can see the images given here, the three different configurations. Here you can observe the variation in different configuration of armchair, chiral and zigzag. Next, we'll see. Currently, scientists are trying to make carbon nanotubes in high yield with high purity. High purity results in same physical structures of the carbon nanotubes, so which will result in similar physical and chemical properties. So due to the similar properties, it is easier to predict their behavior so that it would be ultimately useful for possible nanosensors. What is nanosensors? These nanosensors are behaving like semiconducting material in microelectronic circuits. They detect even a small changes in electric current and also register chemical reactivity or changes in air pressure and temperature. Moving on to the properties of carbon nanotubes: mechanical properties, electrical properties, optical properties, and thermal properties. So these are further discussed. Coming to the mechanical properties of carbon nanotubes, they are known to be one of the strongest material in nature. And carbon nanotubes are nothing but hollow cylinders of graphene. Graphene is a single layer of graphite. These graphene sheets have 2D symmetry. So carbon nanotubes by geometry have different properties in both axial and radial direction. And it is known that carbon nanotubes are very strong in the axial direction. Coming to the electrical properties of carbon nanotubes. Metallic nanotube can carry an electric current density of 4 into 10 power 9 ampere per centimeter square. So this is almost 1000 times greater than those of a metal like copper. And when we classify it based on the configuration, if n is equal to m, the nanotube is metallic. For n is not equal to m, and if the n minus m is a multiple of 3, and those materials is quasi-metallic. And we know this armchair nanotubes are in the configuration of n comma n, that is m and n are equal, so they are almost all are metallic in nature. Let's see the optical properties of carbon nanotubes. These materials interact with electromagnetic radiation, and it shows peculiar absorption, photoluminescence, and Raman spectra. An application of carbon nanotubes in optics and photonics are less developed, and some properties may also lead to tunability and wavelength selectivity. And potential applications that have been demonstrated include LEDs, bolometer, and optoelectronic memory. Coming to the thermal properties of carbon nanotubes, these are expected to be very good thermal conductors, exhibiting a property known as ballistic conduction. Ballistic conduction is nothing but uninterrupted movement of the charge carriers for a longer distance. So now we'll see about how to synthesize this carbon nanotube. In this video, three methods are discussed. The first method is arc discharge synthesis, the second one is laser ablation method, and the last one is chemical vapor deposition. So we'll see each of the method one by one. So the first method is arc discharge method. So we'll see what is going to happen here. So this method is going to create CNT through arc induced vaporization of two carbon rods. So if you see the apparatus, so there are two carbon rods, the cathode and anode, and the distance between these two are almost approximately equal to 1 millimeter, and this is enclosed and it is filled with inert gases, usually argon or helium at low pressure. So here we are going to supply around 25 voltage across the electrodes. So now what will happen? From the positive electrode, the atoms will be carried to the negative electrodes and it is deposited here. As you can see, this is where the carbon nanotubes are formed. So if there is no catalyst used, we get multi-walled nanotubes. When we use catalysts such as cobalt, as a result, we will get single-walled nanotubes. The next method is using laser ablation method. So here, the starting material is graphite with traces of cobalt and nickel. This acts as a nucleation site in the formation of carbon nanotubes. So what's happening? We'll see. A pulsed laser beam is focused on the surface of the target. So this target which we are using here is graphite. So what happens? Argon moves carbon atoms to cool copper surface. This is the copper surface where they condense and form nanotubes, which are of the diameters 10 to 20 nanometers. This material produced by this method appears as a mat of ropes of diameter 10 to 20 nanometers. So each rope primarily consists of a bundle of single wall carbon nanotubes aligned along the common axis. So the third method is chemical vapor deposition. Here, the starting material is hydrocarbon gas such as methane. This gas is heated at 1100 degrees Celsius, causing it to decompose and release carbon atom. These atoms will condense on cool substrate to form nanotubes. So in chemical vapor deposition,
This substrate surface contains metallic traces like nickel. These act as nucleation sites for the nanotubes. The advantages of chemical vapor deposition is that using low temperature range and low power, high yield is produced. This technique can be used to produce both multi-wall carbon nanotubes and single-wall carbon nanotubes. This depends on temperature, wherein the production of single wall happens at a higher temperature.
Here we can see some of the electron microscopic images of carbon nanotubes. Let us see where and all carbon nanotubes are used. Carbon nanotubes are used in artificial muscles. It is also known as accutators, and it is very widely used in biomedical field, and it is used in nanocomputing and nanoscale electronics. It is used in AFM probe tips. AFM is atomic force microscope. It is used as nanothermometer. It is used in fibers and fabrics, and it is also used in chemical sensors. Thank you.